All right, hello everyone. So welcome to today's presentation, my presentation on the non-negative matrix factorization. So I'm going to give you an introduction and some application of this topic. I will try to not to make it too mathematical. Yeah, but this is rather mathematical topic. So yeah, I will put some effort in introducing many different applications of the NMF. Yeah, and try to make it more like deep learning or machine learning. All right. Yeah. So, okay, let's go. Yeah. So these are the things I'm going to talk about today. So before I talk about the NMF, I'm going to introduce to you the linear dimensionality reductions. So you may be wondering how it is related to the topic I'm going to talk about. And I'm going to give you the reason. So the reason is because first, the linear dimensionality reductions, which we call it LDR as well, is one of the most classical techniques to extract the underlying structure within the data set. So basically, we use this technique to extract some very useful informations from the data given to us. Yeah. So you should be really familiar with this kind of setup because, the deep learning or machine learning, we always deal with many different kind of data sets. Um, and the second thing is this kind of action, which is called the information extraction, is one of the central problem in the data science or actually theoretical machine learning. Um, and the last reason is because the NMF is actually one of the LDR technique. Yeah, so this is an easily interpretable LDR techniques for, in particular, the non-negative data. And the non-negative data sets are very common data sets which we will deal with in our machine learning or deep learning setup. Um, so now I'm going to talk about something more math. Okay. Yeah. So let me give you some the definition of LDR. Yeah. So the LDR basically is something so a technique which represents each data point as a linear combination of a small number of basis elements. So mathematically speaking, if we think those data points as a data set, and those data points are the vectors. So like, for example, if we have n data points, they are vectors in the Rm, then the LDR basically looks for a small number R, uh, which are the which is the number of the basis vectors, or so the basis vectors here we think them as the WK. Yeah, and they are also the m-dimensional vectors, okay? And such that each data point is well approximated by a linear combinations of those basis vectors. Yeah, so basically speaking, if we're talking about, you know, uh, linear algebra, we can present it in this way. Yeah, and the HKJ are the scalars. All right. So now this is a picture to show you how we can do it with m equals 3. So that is the dimension for the vectors. And the r equals 2, which is the number of basis elements. And the n equals 50, which is number of data points. All right. So you can think of that like, in the three-dimensional space, we have 50 data points. And now they are like, just everywhere, right? So now we would like to find some plane which could be spanned by the W1 and W2 and which approximate all these points. Yeah. So now I would like to talk about something called the low rank matrix approximation as well, because the LDR is basically equivalent to that. All right. So you can see that this is the matrix consists of all those xj, and they are the column vectors. Now we take them as column vectors. So now we get a m by n matrix here, and is approximated by the LDR techniques, approximated by this product. And this product, you can see that this is a m by r matrix, which are the so it consists of the columns as the basis elements, the WK, and then the H is the scalar the matrix of scalars, I should say that. So the columns there contains the coordinates of the data point with respect to the basis. So basically, the LDR provides a rank R approximation of X. Yeah, so in the form of WH. So typically speaking, we want the R to be much more smaller than the minimum of the M and N. Yeah, because in this sense, we are talking about how we can use the LDR and R or the LRMA to compress the data. And with a little bit computation, you can see that the R has to be less than the M times N over M plus N. Yeah, because originally X has like M by N entries. So there are M by N data points. Now, and we can see that the product of WH, those entries all together, the W has N by R entries, the H has N by R entries. So we don't want the total number of entries in the WH to be more than the number of entries in X, right? So this is the conditions. But now if the X is a sparse matrix, which has very few number of non-zero entries, then our condition has to be more restrictive. Yeah, so we need this. The R is less than the S over M by M times, M plus N, all right? Yeah, so so in order to compute the W and H given the X and R, then we need to devise some kind of error measure, to so that the WH minimize it, and so that we can talk about what this mean by the approximation, right? So we want it to be well approximated by the W and H, the product of the W and H, right? Yeah. So now an example is to consider the square Frobenius norm of the residue. So basically, we consider the difference between the X and the product. Yeah, and then consider the matrix norm. So this is the Frobenius norm. All right, and we would like it to be minimized by the M and H, the W and H. Sorry. Yeah. So in this case, the LRMA is basically equivalent to something called the principal component analysis. And we abbreviate as the PCA. It's also a very common technique for data analysis. And this is common because we can use a very standard way, which is called the singular value decompositions to do that, to solve this problem. Yeah, but certainly we could have many other kind of LRMA. All right. Yeah, the low rank matrix approximations. Yeah. All right. So gosh, those abbreviations are really hard to pronounce anyway. Yeah. So it depends on the choice of the error measures and also the constraint we consider. So now if we choose a different kind of EM, then we will have a different kind of problem, all right? So but this choice basically depends on the noise statistic of the data. So if we choose the least square, so which is the Frobenius norm, that means we assume the noise is basically the IID Gaussian noise. Yeah, so if they're independent and identical distributed. But if we consider the case like, well, some data may be missing or some data may have higher weights, then we can consider the weighted low rank matrix approximations, and which is called the WLRA. And this problem minimize this norm All right, so you can see that it is the weighted norm. All right, the weighted matrix norm. All right, and the weight is a non-negative weight matrix, and the entry would be 0 if the ij entry is missing. So the ij entry of that matrix will be 0 if the ij entry of the data set, I should say, is missing. All right. Yeah. And other case is to consider the absolute norm, the absolute matrix norm, all right, of the residues. And this gives us something called the robust PCA. And this kind of techniques could be used to background subtractions of the video sequences. Yeah, because in that case, the background has low rank and the noise is assumed to be very sparse. Okay. And the other factor we could consider when we consider different kind of LRMA is to impose different constraint on the factors W and H. Yeah, so that would depends on the applications and how you interpret those factors. Yeah, so say for example, if we consider the k-means problem, which means we would like to find or locate the R centroids WK such that the sum of the distance between each data to those centroids are minimized, then this kind of LRMA would be equivalent to the problem in the sense that the factor H has a single non-zero entry in each column, and that single non-zero entry is just 1. And so each column will be corresponding to the cluster centroids, each columns of the W, I mean. Yeah. So now, yeah, we are really ready to talk about the NMF. Yeah, so what does it mean by that then? Yeah, so among all those LRMA models, yeah, the NMF requires the factors to be non-negative. Yeah, so if we impose the different constraint on the factors, the W and H, and they are non-negative, and this non-negativity constraint plays very important role in many different kinds of applications. Yeah, because we can make use of that to make some good interpretations of the result. And also we can extract some meaningful and very easy to interpret components in those non-zero data, non-negative data sets. So the actual problem goes like this. Yeah. So now if we have the data set as a non-negative matrix, and so this is n by n, all right? So all the entries are non-negative. And if we require the factorization rank to be R, yeah. And now we would like to solve the following problem. We would try to minimize the distance measure on the W and H. And the W and H, we require them to be non-negative as well. All right. And here the W will also be the matrix of the basis elements, and H will also be the matrix of the scalars. Yeah. So you may be wondering, well, this is not really like factorization in the linear algebra sense, because usually if we're talking about factorizations, we talk about x equals like the product of the W and H. Yeah, but we're not using that meaning in this way. So in my presentation, or actually in the book I take a reference of, we use the non-negative matrix factorization for these approximations. Yeah. Someone will call this non-negative matrix approximation, but we don't. Yeah. So for the exact case, we call it exact NMF. So exact non-negative matrix factorizations. Yeah. So now the objective function of this problem, we also call it error measure, is given by the following map. Yeah. So the choice of this error measure is really crucial, and it depends on the assumption made on the noise, as you know. So most of the EM in the NMF problem will have the following form. So it basically just give every entry the same considerations. So that will be the summation of some kind of like a distant function between the entries of the A and B. Yeah. And we also have the condition that that would be 0 if the entries there, the X and Y, are the same. All right. So that would be 0 distant if they are like exactly the same. So, and a standard choice is to consider the square of the X minus Y. So that will basically give us the Frobenius norm case. Yeah. And this is a common choice and also standard choice because there are two main reasons. So one of the reasons is most of the time we have the Gaussian noise and IID Gaussian noise. All right. The second reason is it will give us a smooth optimizations. Yeah, and we can make use of many different kind of smooth optimization tools to solve that. Yeah. So we also have some NMF variants. So some variants use regularizations to obtain new solutions. And so in this case, we may pay attention to some underlying structure of the data sets. So for example, the data set may be sparse, so we have to make use of the regularizations to consider a different NMF problem. Yeah. And the other variants use additional constraints. So maybe like the H we require to be the transpose of the W, and we'll get the so-called symmetric NMF, the same NMF. Or if we require the H to have orthogonal rows, then we get the orthogonal NMF, which is called the ONMF. Yeah, but we won't really go into them too deeply. We basically focus on the standard one. So this one. All right. Yeah. So now, okay, most of the most of the math are almost gone. So let me finish this part. And I'm going to talk about the 4 applications of the MMF. Okay. Yeah. So so I would like to talk about the sparsity as well. All right, because this is a kind of like a very common structure or very common phenomenon we can see from the data set we study when we talk about the deep learning or the machine learning. So yeah, especially if we consider the non-negative data set, yeah, the NMF solutions WH are expected to be quite sparse. Yeah, because mathematically speaking, if we the problem we're considering is actually kind of like the smooth optimization problem with the non-negative non-negativity constraints. Yeah, and by something called the first order optimality conditions, yeah, we can have the following conditions on the X and the gradient of the F. And so now we can see that the xi will be 0 basically whenever the gradient at that entry is 0. Is bigger than 0. Sorry. Yeah. So now, all right. So we are ready to talk about the applications of MMF. All right. Yeah, so basically I'm going to introduce to you 4 kind of application which make use of the NMF. And I'm going to talk about them as like, well, how we can just formulate them using NMF. All right. Yeah. So the first thing is the feature extraction in the set of images. Yeah. So we basically do it in this way. Yeah. So given a set of grayscale images of the same dimensions, and now we could construct a matrix X such that each column, the xj, corresponding to a vectorized gray level image. But how can we do it? Well, so basically we can transform a two-dimensional images. We can transform the two-dimensional images into some a long one-dimensional vectors, all right, by something called this stacking. Yeah. So basically, if we have a two-dimensional image, we can just, basically divide it into the column of grayscale, and then we just stack them, all right? And then we will get the vector, yeah, as a long column vector, yeah. And so each entry, for example, the xij represent the intensity of the I pixel within the J image, all right? And that will be non-negative, as you know, yeah. And so now, if we factorize the x with the NMF, okay, and if we get the result as the W and H, and they are non-negative, and that would be a LDR problem, and actually NMF problem. And the WK, they are the basis for our data set. Yeah, the XJ. Yeah. So the non-negativity for the W implies that those WK give us the basis images. All right. So they are the vectors of the pixel intensity whose linear combination approximate our input images. And also the H is non-negative, so no cancellation is possible. Yeah, when we construct those input images by the basis images. Yeah. So basically, those basis images correspond to localized features that are shared among those input images. Yeah. And the entries of the H indicate which input image contains which feature. So basically, we can look at this picture, and this is the case when the R is 49. And well, so we have we make use of the 2,429 images with 90 times 90 pixel each as the input images and do the training. Yeah. So we have a very nice paper here. All right, I'll show you later. And basically, I based on my presentation based on this paper and another book, the book called Non-Negative Matrix Factorization, and you will see that later. And now you can see that on the left is column of X, reshaped as an image. And in the middle, there are 49 columns of the basis of W and reshaped as image and display as 7x7 group. And you can see that they are like the noses or the the eyes or the mouth and things like that. Yeah. And now if we consider the reshaped columns of H as a 7x7 group, and then we just do the multiplication here, then we will get an approximated input image. All right, as the original image is like that, and this is the approximated one. Yeah. So this is an example for the feature extraction in the set of images, and another easy example is called the synthetic swimmer dataset. Yeah. So the things is like that. So the XJ, the column of the data set, are the vectorized images of a swimmer, and the swimmer has 4 limbs, and they take and those limbs take 4 different positions. And so we have in total 256 images. And the N here we take it as this one. This one. And so we can just solve this problem with an NMF of rank 17. Yeah. And now we will have the following WK. Yeah, so we have the body and we have the 16 different positions of those 4 limbs. Yeah. So these are some sample image of the swimmer data set. Yeah. Yeah, I talk about this easy problem because actually there exists several exact NMF with lower rank, which is rank 16, to solve the same problem. Yeah. So sometimes we could use the exact NMF for doing this kind of problem, but most of the time we will just consider our NMF, which is the approximations. Yeah. So that would be another problem. So that would be more like a math problem. when do we have the exact NMF or when we do not, right? Yeah. So, but most of the time we'll just make use of the, approximations, and that will be enough. And another kind of application is called the blind hyperspectral mixing. Yeah. So this is also like an image processing problem. So a hyperspectrum image measures the intensity of the light within a scene for many different wavelengths. So usually those wavelengths are from like 100 to 200 wavelengths. And now, so we can see that for each pixel, a vector of intensity is recorded, and that is equal to the fractions of the light reflected by that pixel. And that would depend on the wavelength. Yeah, and we call it the spectral signatures of the pixel. Yeah, and now our blind hyperspectral and mixing problem is talking about like given such image, we would like to recover the materials presented in an image and also the proportion of each of those materials in each pixel. Yeah. So basically those materials, we would call them N members, and the proportion, we call them the abundance. Yeah. So let's look at this picture first. Yeah. So this picture shows you the linear mixing model for the hyperspectral imaging. And what does it mean by that? So under this model, the spectral signatures of a pixel is just equal to the linear combination of the spectral signatures of the materials it contains. So you can see that here, like if that pixel contains like 70% road and then 30% glass, yeah, and then we just do the linear combination of both of them, of the spectral signatures of the pixels, all right, and then we get the end result. Yeah. So in this sense, then we can just let the xj be the spectral signature of a pixel. And now we can see that our blind HU, all right, so our blind hyperspectral and mixing problem boils down to a NMF problem of that matrix, yeah, the X, which consists of those xj as the columns. So now if we decompose the X in this way, yeah, using the NMF, yeah, take this approximation, then we could notice that those WK, they are the columns of the matrix containing the spectral signatures of the M members. And the HKJ, this matrix will give us the abundance of each M members in each pixel. Okay. So to be more precise, that would goes like this. So now here we have the case of R equals 6 NMF problem. Yeah. So we distinguish the materials as the road, the dirt, the trees, the grass, and the rooftop 1 and 2. Okay. Yeah. So this is a very common way to do the blind HU. Yeah. So that image is taken about a Walmart somewhere, okay, in the Texas. Yeah. So we have 162 spectrum bands, and the pixels dimension is 307 times 307. Yeah. So this kind of data set, we call it an urban data set. Yeah, and each factors correspond to the spectral signatures of the M members. Yeah, so each of them, so 6 of them. Yeah. And we also have the abundance map, which is a row of the edge, okay? And we can reshape as an image on the figure. And now we can see that the light tunes represent the high abundance. So we can see that those here, those are the high abundance for that kind of materials. Yeah. So usually we just use this 6 kind of materials for the urban hyperspectral image. Yeah. And in particular, this rank 6 NMF would do the job well because it basically explains more than like 95% of the data of the urban hyperspectral images. Yeah. So to be more mathematics, that means the forbidden norm of the residues is less than or equal to the 0.05% of the Frobenius norm of the original data set. Yeah. So the image I extracted from the book, all right, and we'll show you the reference later. Yeah. And the third application is called the task mining, topic recovery, and document classifications. Yeah. So basically here we take each row, the xj, to be a document. All right. So that would be a non-negative vector of word counts. Yeah. So say for example, the xij, that entry is the number of times word I appears in the document J. Yeah. But this is not the only way we construct a matrix X here for the task mining. We can also make use of something called the term frequency inverse document frequency, right? TFIDF. All right. Yeah. So you can search for that kind of techniques actually gives us a way to give more weighting for like some specific terms in some documents. Yeah. So it depends on your needs and your applications. So this kind of model, we also call them the back of words model. So the positions of the word in the document are not taken into account. Yeah. So if we take into account of the positions of the words, then the problem will be more difficult. So here we consider the simple case first. Well, oops, yeah. So now you can see that if we do the NMF on this, then we will get the solutions. So the WK, they are the best of words. So they basically the vectors of the word counts. And we can also see that because the R is much smaller than the N. So each WK will be used to reconstruct many documents. And basically we call them the topics, okay? And also we can see that because it's non-negative, so no cancellation is possible. So each WK will contains the words that appear simultaneously in many different kind of documents. So this is why we call them the topics. Yeah. So we extract the topics out of those documents in this way. And now we can also see that those HJ, so the H matrix, they indicate us the importance of the topics discussed in the corresponding documents. So they give us some kind of like the weighting for the topics in the documents we study. Yeah. So in picture, we can see that is basically like, well, so we consider those documents like as column vectors. All right. So we can see the number of row is basically the size of the dictionary. And then we have this kind of NMF problem. We solve it and we have the topics as the columns here. And these are the weight of each topic to reconstruct those documents. Yeah. So we can also see, we can also take it as like the classifications of the topics. Yeah. So basically we can see that. Yeah. The XJ, they are the set of words. Yeah. The XIJ is just the importance of the word I in the document J. Yeah. And so now those WK are the topics. And you know that those topics will be much smaller, right? So this is how we extract the data. Yeah. And this is what we want the deep learning or the machine learning algorithm do that for us, right? Yeah. And the last application is called the audio source separations. Yeah. So we talk about this in this way. So given an audio signal recorded from a single microphone, yeah. So we would take the single microphone case because it's the simple case. Yeah. If this is the like a the recording machine is not like just a single microphone, then we will have to consider another more like convoluted problem. Anyway, so now the magnitude spectrogram can be constructed in the following way for that kind of audio signal. So we basically split the signal into small time frames with some overlapping. So usually it's 50% overlap, and then we multiply each frame by some window function. Yeah, say for example, the humming window, to avoid the because we truncate those signals, right? So we would like to avoid the artifacts due to the truncations. And then we take the Xij to be the magnitude of the Fourier coefficients. We're talking about audio signals, right? So we can actually like take the Fourier transformations of those time frame. Yeah. So we can take the short time Fourier transformations to be more precise. So now the Xij will be just the magnitude of the Fourier coefficients for the jth time frame at the I frequency. Okay. So now our goal for audio source separation is we would like to blindly separate the sources from that compose the signal. Yeah. So in picture, yeah, so I will talk about this later, but I would like to show you the picture first. So this is kind of like the picture how we want to deal with the signal. Yeah. So this case, we're talking about a simple one. So like the this is an example. The Mary had a little lamb music or whatever. Yeah. So we have this simple monophonic signal case like this, and we can see that this sequence is composed of 3 notes only, the C4, D4, and E4, and it activates in the following way: the E4, D4, C4, D4, E4, D4, E4, right? So we have like 1, 2, 3, 4, 5, 6, 7 notes here, right? Yeah. So we have 3, in this case, we have 3 main sources. Those are the piano notes. So they are the C4, D4, and E4. Yeah, and in this case, each WK will be the signature of each note in the frequency domain. And so those HKJ, so those entries in the H, indicate when a note is activated. And we also actually have a 4th source because we have some noise. So for example, the hammer noise within the piano. Yeah. So this is how we do the NMF and what we get. Yeah, so we have 4 so we can see that we have 4 sources here. And this is the when the note is activated. Yeah, so the H indicates that. Yeah, so as you can see, this is how we decompose the piano recording of the Mary Had a Little Lamb. Okay, yeah. So the H indicates the when each note is activated, and all things we record them in the dB. Yeah. And by the way, yeah, I didn't mention that the separation problem is an NMF problem under the following 2 assumptions. So we have to make some assumptions so that we can make use of the NMF techniques to solve it. So one of them is the spectrograms of the sources are also low rank. The spectrogram of the mixture is a non-negative linear combinations of those spectrogram of the sources. So this is why I take this as the example. And as you can see, those sources are basically just rank 1. Yeah, those 3 main sources, right? Yeah. And this obviously is a non-negative linear combination of those sources, this piece of signal. Yeah. So, all right. Okay, so now we have the conclusions. All right. Yeah, sorry about I know this presentation is a little bit long. Yeah, a little bit over time. But yeah, I have too many things to talk about for that. Anyway, so NMF in conclusion is a linear dimensionality reduction techniques with the non-negativity constraints on the factors, and it could be used to extract meaningful components in various applications. And the Li and Shang paper were able to popularize these techniques. All right, and you can definitely check it out. Yeah, it's on Nature and is open access, I guess. So you can really like take a look of it. And in this paper, they also show that the NMF is really versatile and it can be used in many different setups. Yeah, and also basically in theoretical machine learning, we always talk about this. Yeah, because you can see how many applications we can make use of that. Yeah, in related to the deep learning or machine learning. Yeah. So to summarize my presentations, so I think even if you're not interested in the theoretical aspect of the machine learning, you should learn something about the NMF. Yeah, either the how we can use it or how it is related to the other kind of problem in the in the machine learning. Yeah, because that may give us some insight in how we decide the some machine learning algorithms. Yeah. So, all right. So these are the references. Yeah. So I basically use this book. Yeah. And but my presentation also based on this paper. And this is also the very important paper in the NMF. And thank you. Yeah, that's all. Yeah. Yes. Sorry to be overrun. Right. So any questions? Any problem? No. Right. Mhm. Oh, so you mean the first one? First, the feature extraction, right? This one, right? Oh, yeah. So basically we can look at this example. Yeah. So we make use of the CBCL is something called the child I don't remember the non-name for that, but there are images of different people and um one of the machine learning or the deep learning problem. Oh yeah, the this is the short form for the child behavior checklist. Okay, so anyway, so yeah, so one of the main goal in the machine learning or the deep learning is to extract the features from a big set of data, right? Yeah. So now if we have many images and if we would like to know how they share some features, so like, well, so some of them, some of the people in those images which may share the same shape of the eye or same shape of the nose, or they may have the same kind of mustache, may have the same shape of mouth and things like that. And now we would like to use a lower dimension of data set, which is the W we would like to search for here to present all those features so that we do not really need to make use of all those images, or we can actually extract the information within the images and do for like use them for further actions. So maybe, well, we can make use of them to, train some kind of AI to distinguish the different race of the people, or maybe, well, to distinguish, well, the gender, to distinguish the age, or things like that. Yeah. So these are the further applications. And how we can do it is, well, it's just like what I mentioned here. We basically we focus on the grayscale image. Yeah, we could do the colored rise image, but that would be the RGB. Yeah, so basically, if we can do it for the grayscale image, we could do the RGB. And now we assume the matrix, they are the data, right? So each column correspond to one image. Yeah. So like in this case, we have a really, 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 really big matrix, as you can see. Yeah. So the number of images or number of data points we have is the dimension of the matrix, basically. I mean the number of rows, I should say. Number of column, my bad. Number of column, the n, all right? Yeah. And then the number of rows is actually the dimension of the image. So like if we have the image as 19 times 19 pixels image, then this 19 times 19, which is, pardon me, I know I'm a math major, but I'm really bad at this kind of calculation. Sorry about that. Yeah, so 361. All right. So yeah, 361 would be the m in this case. Yeah, so we will have those vectors as the 361 dimension vectors, column vectors, and we have 2040 2429 columns. Yeah, and that would be our x. And now our LMF, our NMF problem will uh be uh, uh will be to factorize this x as a product of W and H. Okay. Yeah. So now the W in this case are like this. Yeah. So we basically, uh, uh, we let the R to be 49. Okay. Yeah. So we let the R to be 49. So basically we only have like 49 columns of the W. Yeah. Okay. And W has the same uh, dimension as those XJ. So they will always also be 361 dimension column vectors. Yeah. And now the H will be yeah, we put it in the 7 by 7 girl. Yeah. So actually we don't need to put it in this way. We can actually expand all the things like what the original matrix is. Anyway, but now the H there, and as you know, the H will have the number of column will be the same as the X. Yeah, so there will be like 2,429 columns of the H. But the number of row, I mean the dimension for each column vector here will be just 49. All right. And now if we just multiply them, and then we'll get a result image, right? And that result will be the approximation of our original output, so original input. All right. Yeah. So this is how we yeah, so this is how we get the this thing. So this is one of the column. Yeah, this is just one of the column, I should say. Yeah, this is one of the column. So this is one of the column of the WNH. All right. So you can see that this is an approximation of that. And now we have many, many, many columns like this. And we have many, many columns like this. All right. And then that would be the NFF problem as a whole. Yeah. So did I answer your questions? Yeah. Yeah, kind of. Yeah. So it really depends on the norm, I mean the error measures you take. Yeah. So if you take the Frobenius one, which is the standard one, then you would get results like this. Yeah, but certainly you can think of the others. But usually for image, we just assume the IID Gaussian noise, I guess. So this is why we take the error measure as the Frobenius one. Yeah. Okay. Any other questions? Yes, yes, yes. Oh, yeah, sure. Yeah. Okay. Yeah. Yeah, yeah, yeah. Okay. Yes, this one, right? Sorry about that. Yeah, okay. Yeah. So the test analysis, basically like now you take the data set as some documents. All right. So now the matrix X, each column correspond to one document. All right. So different of documents will contains different number of words, and those different number of words will be related to different topics, right? Yeah. So now, what we do here is, we basically would like to use the NMF techniques to factorize the X and as a product of W and H. And now if we do it in using the NMF setup, then we will get a um, matrix W, which we can see it as the best of words. Yeah, so the columns of the W here will be just the vectors of the word count. And those word counts are actually giving us those topics. All right. Yeah. So maybe many documents there are talking about deep learning. All right. And then so the and talk about the deep learning and the things related to the deep learning. And so now the W column there would be maybe the vectors of the word count in that topic, the deep learning. All right. Yeah. And then the H would be the basically the coefficients matrix, yeah, or the classifications, which gives us how important of each topic in each document. Yeah. So if we look at this thing, so you can see that this XJ is a column. This is one document. And now we can try to factorize this document as the summations of the topic multiplied by the weighting, right? So they are like the importance of that topic in this document. But the whole picture is we have many, many, many such columns with many, many documents like that. If we can solve the NMF problem, then we can extract the topics from those documents and how they are important in each of the documents. Yeah. So the big picture will be like this. Yeah. And one thing you need to note is the dimension for each columns corresponds to the size of your dictionary. All right. So this is another problem. Yeah. So you may have to, make a good, um, just make a good choice of the dictionary. Yeah. So it really depends on, the documents and how you would like to use these applications. Yeah. So now the W will be just here. Yeah. These are the topics. Yeah. Okay. So, did I answer your questions? Is that clear? Yeah, so one column, one document, and if you just look at that column, then you can think is that column vector, the column vector is just a linear combination of the basis elements, all right? Yeah, you can see it like that. Yeah, and these are the basis elements. Yeah, the WK. Mm-hmm. Yeah, you can say that. Yeah. But um a better description is like we do the data mining of a collection of documents. Yeah. So for example, those documents may be from a particular subject, and we would like to um discover what are the words found more frequently in those documents, and we would like to uh just find the topics, the features topics within those documents. Yeah. So it's more like, yeah, it's more like you're creating a constructing a dictionary. Yeah, but in the sense of like topics, but not like dictionary means you have the words and the meaning for the words, but now it's more like you have a collection of the documents for one subject. Now you would like to see what are the features of that subjects. All right. Yeah. And so that you can make use of that for like, you know, later use or the other applications. Like, well, for the LLM to to learn the meaning of the input documents or things like that. Yeah. Yeah. All right. Is that cool? Is that cool? Great. All right. So any other questions? Any other questions? Problems? Hmm. All right. Mm-hmm. 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 Mm. Yeah. Yeah. Uh, yeah. Oh yeah. So here the applications I present them in a rather simple case. Yeah. Actually, if you would like to deal with the more difficult case, we could have some other ways to do the modeling. Yeah, and we have many different kinds of MMF as well. And we can impose some other constraints. We can make use of the regularizations on the error measures. And those kind of ways will also provide us better resolutions to what you have just said. So maybe, yeah, so if we would like to consider the order of the words, maybe like in the um task mining problem, or if we would like to um you know consider, take into account the facial features at a particular positions. Yeah, we could actually have some kind of further consideration on that. But yeah, I just didn't mention them. Yeah. So that book, I mean, this book is a really, really, really useful and important book, and you can actually check it out. And my presentation only present basically the chapter one of it, not really basically chapter one. It's just the introduction of that. so so yeah, this book contains so many other informations about basically about the answer to your questions. Yeah, so you can actually check it out if you want. Yeah. Yeah. So I just don't have time to cover that. Yeah, sorry about this. Because originally I was like, I would like to cover like one more chapter, but it seems that I cannot. So as you can see, my presentation has been like 50 pages. So I can only talk about like the introduction and then some simple applications. Yeah, but each application has some really like further investigations. Yeah, just on the book. Yeah. So there are many different kind of papers or references which are given by this book, and they're, for different kind of application, not only these four as well. Yeah, these four are the more important and more popular application of NMF. Yeah. Okay. Okay, cool. So, any other questions as well? Yeah. All right. So, if there is no other questions, I think that I would just call it a day. Yeah. Hmm. Hmm. Yes. Yeah, I would like to, yeah, I would like to enter them now because I have to recall what they are. Yeah, so give me a second.